let's look at how these things then look like. So this is your idealized solar cell operation. So it has your open circuit. This is a short circuit current, and the short circuit current is relatively constant till a point where it starts to decrease very quickly to 0 at the open circuit voltage, and this point is the maximum power point where the corresponding current and voltages are given here. This is somewhat lower than the ISC because the voltage is continuing to increase. So the maximum power point will be, the current corresponding to the maximum power point will be slightly lower than the short circuit current. And this is the fill factor definition as we discussed. This is the idealized constant current source. Okay, the actual power for an idealized source is the area of this rectangle. Correct. And here the maximum power point, this is the area of this rectangle. So the ratio of these two areas is this one fill factor. This is your N side, this is your P side. Sunlight is hitting your PN junction diode here. Okay. So let me explain what is going on. Alright. This is your solar cell operating, P side, N side. Electrons are flowing this way. So the current is obviously flowing the other direction. Okay. So the main current flow is in this direction. This is the total light current. The current that is produced due to the operation, the generation of electrons and holes due to sunlight. Okay. So IL here is the light induced current. Okay. Now you notice that ID is moving the opposite way. Okay. So the basic idea here is, if you remember how the modules look like, you have this kind of a structure, right? This is your zone, and electrons are being generated here, holes are being generated here, holes are moving in this direction, electrons are moving in this direction. This is the N side, this is the P side. Okay. And this is your Fermi level EF. Alright. Now, when the temperature is high enough, it is possible for some electrons, and because you have an external voltage applied, right, because of the presence of a load. So you have a load L here, and there is this external voltage, positive side to negative side. Okay. So because of this external voltage, some electrons will have the ability to jump from the N side to the P side as well, given that it has sufficient energy. Okay. So whereas the actual major flow of electrons due to the presence of photons will be a flow of electrons this way and a flow of holes this way, so that the main light current will move the main light current will move this side because of the presence of this external voltage across the load that will generate enough energy to have a small amount of current developing the opposite way. That is, some electrons will be able to jump from this side to this side, and some holes will be able to jump from this side to this side. So there will be a smaller amount of dark diode current that will also be formed. So this is this dark diode current. Okay. In general, when a PN junction diode is unlighted, you have an external voltage is applied, and this dark diode current is produced after a certain point when sufficient voltage is through. Okay. So this dark current will also be generated because of this presence of this voltage. Furthermore, what we want here is that these electrons will only flow through the external circuit and go this way. Okay. But often what happens in these materials, at the edges there are impurities. Okay. Impurities, crystal defects, etc., through which these electrons can have a short path to go to this side. Okay. So you should think of this as a material, right? So this is the N side, this is the P side. Okay. A lot of electrons have come over this side and a lot of holes have generated over this side, and we are using the conductor base to flow your electrons this way. Okay, so the current is flowing this way and the electrons are moving this way. Okay. Now suppose there are at the edges there are impurities in this system. So the electrons can have easy access to the P side through the edges or any crystal defects that exist. Okay. So this effect is called shunting. So if the electrons can move from N side to P side, bypassing this potential gradient through these crystal defects, then obviously those electrons are being lost to the external circuit. Okay. So that is called an internal shunt current that also reduces from the overall current. Okay. So what you can then get is IL is the light induced current, ID is the oppositely directed dark current, diode dark current, ISH is the internal shunt current due to edge effects, crystal defects, etc. Okay. And RSH is the shunt resistance, so this shunt resistance should be high so that this shunt current is small. So we want to decrease the shunt current, so the resistance to this kind of a shorter route should be high in your idealized solar cell. Okay. And RS is the internal series resistance. Okay. So this internal series resistance is the resistance of these electrons to move to the collector area at the top and the holes to go to your bottom collector area. Okay. So internal resistance of this material. Okay. So then what you get is finally the total current I. So this is the external circuit. Okay. This side is the external circuit. The total current I in the external circuit is light current minus dark current minus the shunt current. Okay. So I is the total current in external circuit. I equals to I light minus I dark current minus I shunt current. Okay. Now what is the shunt current? If you see here, the external applied voltage is V and the resistance is RSH. So I shunt current is V minus I into RS by RSH. Okay. So the external voltage plus this current into the resistance is equals to ISH into RSH. Okay. So basically the voltage equals to ISH into RSH plus I into RS. Okay. These two together. I into RS, ISH into RSH. Okay. So your total current I is light current minus dark current minus V minus I R series by RSH. Okay. All right. Remember that external load RL is given by V by I. So if this load L has a resistance RL, this is given by the external voltage by the external current V by I. So then, what are the requirements of a good solar cell? Good solar cell. Based on this analysis, the light current IL should be maximum. The dark current ID should be minimum. Okay. The shunt current RSH, the shunt resistance RSH should be very large. And number 4, RS should be small. Okay. So if these things are satisfied, then you get RS is small, so this value decreases, so your current will be maximized. Okay. And shunt current resistance should be large, so this current should go to 0. So these are the main requirements of a good solar cell. So I will stop here today. We will discuss further in the next class on how to evaluate the efficiencies and how to ensure that these requirements can be met by a good quality solar cell. Thank you for attending the class, and we will see you in the next time. Thank you.